Greetings everyone. In this two-part video series, I'm going to demonstrate the 4 types of malware analysis on a malware-like file created for demonstration purposes. Those 4 types are static file analysis, dynamic behavioral analysis, static code analysis, and dynamic code analysis. This video will cover the first 2 parts. The second video will cover the next 2 parts. So let's begin. The file that I'm going to be analyzing here is this example 5.1.exe, which is included in a link in the video description. Now, I'm going to start with static file analysis. Typically, the first thing I do when I'm doing this kind of analysis is to see what other information exists about this file, just to save myself the trouble, because if someone else has already done the analysis, all I really need to do is to verify their results. So in order to do that, I first need to get the hash of the file. I need a common search term to use, because a file can be renamed. So to do that, I've got this tool here called Calc, which is a very nice tool, standalone exe, no installation required, and I can generate what types of hashes I want. And then all I have to do is simply drag the file into here, and I have a hash. So I'm going to use the Md5 hash simply enough and search 2 things. The first thing I'm going to search is virus total. And I want to find that virus total has already seen this malware before, and it has 40 out of 68 hits. And you can look through here and you can see if the antivirus engines have any kind of consensus on what this malware is, because that can give you something else to search on. Here you can see everything is pretty much Trojan generic. Generic, agent, Trojan, whatever, unsafe, unclassified malware, so really not very helpful here. They're saying it's malicious, but there's really nothing to pivot on, no new indicators we can gain. We can look at the details here, we can get some other information, but we can get all of this through other means. It's saying that it's packed using Armadillo. That's incorrect in this case, but regardless, we will find this information through, like I said, other means. We can look at the community and see what people say about it here. So there's a link here to some other resource, more stuff here as well. So you can get some information on what the community is saying about it if they've seen it before, and which in this case they have. Okay, so now let's turn to Google, and I'll search for the hash there. And we can see, okay, here is the virus total results. There is a hybrid analysis result, which you can see I've already looked at. So let's look at that again. Hybrid analysis is a very good free online sandbox, although using the free version, they hide certain indicators from you, but it still gives some useful information. So it gives us some generic stuff here. Okay, identified as malicious by AV engines, we already knew that. Input sample dropped a file, okay, writes a PE header to disk, so that's interesting. We can tell it's probably a dropper just from this information. Accesses browser information, unusual entropy sections, meaning perhaps it is in fact packed. Detect the presence of a debugger, okay. It drops executable files again. So you can get some pretty decent indicators here. And the point of this really is just to give you an indication of what to look for when you're doing the next stage of your analysis. So let's see what else Google has. Report from Manalizer, a different type of analysis sandbox. Okay, something saying it's a Trojan downloader. So as you can see, you get some pretty basic, pretty decent information from this. And again, the main point of this is just to inform your future analysis. Okay, so let's use our next tool here, which is bintext. Bintext is a simple string search. So you see what interesting strings we can find in the malware. Okay, so I'm going to scroll down through here. We see command.com and comspec. Comspec is the Windows environment variable referencing the command prompt. So it probably invokes the command prompt to do something. That's good information. Error messages, not particularly important. We've got Win32 API calls, which we can get from this tool, but there are better tools for this. I'm going to ignore this for now. Let's see what else we got. Okay, so here are things that look like commands, and here's a registry key, software, Microsoft XPS. This is definitely in the format, at least, of a registry key. HTTP 1.0, so perhaps it performs a web request. These things here, nothing, download, upload, sleep, this seems very similar to commands to me, so perhaps this is commands that the file will accept once it's running. We also see cmd.exe/cdel and pipe to null, so it looks like it does in fact invoke the command prompt, and it's going to delete something. And that's pretty much all we can gain from this. So from here we've gleaned that it spawns a command prompt, so when we do our behavioral analysis we can look for that kind of thing. So again, what we're doing here is simply giving us things to look for when we do our next stage of the analysis. So to do our next thing, so the next thing we should do is look at the import table using this tool called Cmf Explorer. So I'm going to open the file here. I'm going to go to import directory, and what this will tell me is what libraries this file invokes and what function calls it makes. So as you can see, look at kernel32.dll, which everything has to include, but we can see what functions it uses. So sleep, perhaps anti-analysis, read-write file, okay, pretty typical stuff. Get current process, terminate process, exit process, so some kind of process manipulation. We don't know what process it's doing this with, but hey, it's more information. And let's see what else there's of interest here. Not really anything useful, so let's keep going. Here we see OpenSC Manager A, open service, create service, close service handle. So clearly it looks like it's going to create a service, perhaps as a persistence mechanism, so that's a good thing to look for. This is a bunch of registry manipulation functions: delete, create, set value, open key, query key, and so on. Also delete service. So service manipulation and registry manipulation. Again, just more things to look for. Shell execute A. This is kind of like a arbitrary command execution function where it'll simply run whatever you pass to it. So it's going to run some kind of command. Again, another thing to look for. And then here we have winsock. And the interesting thing about winsock is this DLL is invoked by ordinal rather than by function name. So we don't know what functions it's using. In order to figure out what functions it's using, we have to look at the DLL itself, which of course I have conveniently saved here. And if we open the DLL and we look at its export directory, we will see that there is these ordinals here, and then it ties them to the function name. So through this mechanism, we can associate which functions are actually being imported by consulting the export table of the DLL. So let's look at an example. Here we have ordinal 3, 4, and 9. So we can go to our DLL here and we can look at the ordinal column, not the name ordinal column, the ordinal column. So we've got close socket, connect, and htons, which is host to network converter function. And so basically through this means you can find what functions are being imported, even if they're being imported by ordinal, unless the name is not there. Okay, so that's pretty much all we can get from this. The final thing that I want to show you as pertains to static file analysis is what happens when a binary actually is packed. So here I have a packed version of this binary, which is simply packed using UPX. And I want to do a string search on this file. And you're going to see here that some of our strings are mangled due to the packing. So here you can see comspec survived, but this was command.com, which has been cut off. If we keep going here, some of the import functions have also been cut off. These are the this is the remnants of the registry key. You can see all now it says is authware. This was HTTP 1.0. You can see the H and T were cut off. These are the commands. You can see it mixed download and upload, and the other commands are lost. Here is the remnants of my cmd.exe / c delete pipe to null, and then here is the URL. So basically the point of this is that packing will mangle strings and make it more difficult to determine information through static file analysis, and you basically have to unpack it if you want to get this information. Finally, I will also open Cmf Explorer and look at the packed version. If we look at the import directory, we can see that it shows far fewer imported functions now, because the import address table, which this tool parses, has been mangled by the packing function. So we see far fewer functions now because of that mangling. And then finally, we can look at PEID, which is a pretty basic tool to help identify packers. And if we go here and we then do, whoops, that's not what I want right now. I want to do a deep scan, and we'll see that it says it is UPX packed, which is correct in this case. And we can go a bit deeper here by looking at the entropy. So we can see 7.89. Shannon entropy, which is what this uses, is out of 8. So 7.89 is very, very high, and thus it is pretty obvious that this is compressed or packed or encrypted in some capacity. And again, EP check saying is packed. We can also, where is it? Look at the, where is it? Sections. There we go. So this tells you the section names. Now UPX is a very obvious packer. It literally names its sections UPX 0, 1, and 2, so you can tell what packer it is. Most good packers that are actually used to obfuscate malware will not be quite so obvious in this regard. But one thing you can also do is you can get the entropy by section. Doesn't want to give me that one. There we go. So this is saying that this section UPX1 is 7.85 entropy. So again, very high, obviously packed. This one here, 2.55, very low, not packed. So using this tool, we can identify packers. Okay, so that's the end of static file analysis. Now let's move on to the dynamic behavioral analysis. So to do this, the first thing we want to do whenever we run malware is to create a snapshot of our VM before we run it. So I'm going to do that real quick here. We're going to VM, snapshot, take, and I'll just call this 4. Okay, good. There we go. Snapshot created. So now we're going to run a few tools. First thing we're going to do is run auto runs to see if the malware establishes any persistence once it runs. So I'm going to go to File, Save, and create my pre-execution snapshot here on the desktop. And there we go. The second thing I'm going to do is run a tool called Registry Changes View, which you can think of as a more modern version of Redshot if you're familiar with that. Redshot works really poorly in Windows 10. This tool is actually of much higher fidelity and it works just great on Windows 10. So we're going to do data source 1 here, create a saved snapshot. Data source 2 will be comparing to the current registry, which we will do after the malware runs. Now the cool thing about this tool is you can specify what hives you want to compare. So you can strip out stuff that doesn't matter. So I'm going to take out this, this, and this. I will create my snapshot, and I also have to do the same thing here. So take these things out, and I will create my snapshot. There we go. Now this tool doesn't really like to minimize, so I'm just going to do Windows D to get rid of it. Okay, so now I have my auto run snapshot and my registry changes snapshot. I'm now going to run my monitoring tool, which is procmon. And oops, let me reset this to default filters. Okay, I'm just going to let this run. And so now, minimize, now we will run the malware. And we see when it runs that it deleted itself. Well, shit, it's a good thing I made that snapshot now, isn't it? Okay, so the first thing I'm going to do here is I'm going to stop procmon's capture. And now, freaking not minimizing tool. Anyway, so now we can do our comparisons. So I'm going to run auto runs. And I'm going to compare to my pre-execution snapshot. And we're going to see that there are no differences. So the malware did not establish any persistence. Okay, good to know. Now we can do our registry snapshot comparison. And here are our results. And so now at this point, you basically just have to go through this and see what in here might possibly be relevant. And this takes some experience to learn what's important and what's not. So like shell bags here, for example, this is just modifying the desktop because that's where my file was. So because it deleted itself, it modified the desktop. I don't care about that. Process monitor, whatever, I don't care. This is garbage, okay. I don't know what this is and I don't care. Now here we can actually find something interesting. This stores timestamps of when certain files are run. And if we look at this one, for example, we will see that it ran Windows System32 conhost.exe, which is the console host, which is what cmd.exe runs when it runs. So we can tell from this that the command prompt was invoked. And we can tell this from procmon as well, but hey, you know, again, just decent corroboration here. This is auto runs, okay, fine. Procmon, we know that. And then there's the malware itself. Okay, so nothing particularly interesting here except for the fact that conhost ran, which means cmd.exe ran. Okay, so we can get rid of that. Now let us look at process monitor. So the first thing let's take a look at is to see if it had any network activity. And we can see that it did not. We can expect network activity because you saw that HTTP string, but we don't see it here, which probably means that the malware was expecting some kind of condition that it didn't get and thus didn't do its full thing. Okay, so now let's look at the registry. Now, there's a lot of registry operations here. We can see that there are 15,000 events. Most of these are really not important to us. So the first thing I'm going to do is start stripping out events of no consequence. What I'm looking for here is changes. So I don't care about things like query key. So I can strip that out. Open key, I don't care. Query value, I don't care. Enum key, I don't care. Close key, I don't care. Enum value, I don't care. Set info key, I don't care. It doesn't do what you think. So okay, now I'm down to create a query again. Don't care. Go away. All right. So now I'm down to the actual change operation. So I've got create key, which just gets a handle to the key, set value, which should be self-evident, and delete key. Okay, good. So now we can actually look at these and see what we have. So okay, let us look at the example 5.1, which is the actual binary. We notice that there are a bunch of set value here on certain browser settings in IE. But interestingly, we did not see this in registry changes view. And so a good question to ask is why? Well, the reason is that this tool catches operations, whereas registry changes view captures net changes. So clearly, this set value didn't actually do anything. It set it to the value it already had. And this is a kind of interesting analysis of how it's good to have both pre and post snapshot tools and real-time monitoring tools. Because the real-time monitoring tools will tell you what operations are performed, but it doesn't tell you, it's kind of difficult to glean from this what the net effect was. Whereas before and after snapshot tools tell you very clearly what the net effect was, but they lose the fidelity on capturing the operations such as these, which in this case are not particularly important, but they could be. And now we've got both, so that's good. Okay, what else do we see here? We see that the command prompt ran, we see that console host ran, we see console host ran again, but none of this really gives us a whole lot of useful information. But we know that the command prompt ran, so presumably something had to invoke it. So what we can look at here is process and thread activity. And if we go to our example 5.1, we can see here, for example, process create, that it created conhost. We can see process start. It again created conhost. And then here we have the conhost actually running. And if we keep going through this, we will find that example 5.1 process create, again here the command prompt, but here we get the actual command line that it invoked. And we see here that it invoked cmd.exe/cdel, the path to the file, and then pipe to null. Now we saw most of this in our bin text, but what we didn't see is what file it performed this operation on, and we see that it performed it on itself. So this is where the self-delete happened. It invoked cmd.exe and said, okay, I want you to delete myself. Now what we don't see here is the actual deletion. So to see that, we can look at the file system activity. So again, here there's a lot of operations we can exclude. I don't care about read file, I don't care about query file, I don't care about close file, I don't care about file system control, I don't care about create file mapping, I don't care about query, I don't care about query again, I don't care about notify, I don't care about query again, so many queries, I don't care. Okay, good enough. I can also strip out the binaries that I don't care about, so explorer.exe, but for the sake of this demo I'm not going to do that. Instead I'm just going to go down here to where we get to our actual file. Alright, so here is an example. You can see here it creating conhost.exe. Now remember, create file in Windows does not literally mean create a file. It basically means get a handle to the file if it exists, or if it doesn't exist, create it and then get a handle to it. So in this case, obviously the file exists, so we're just getting a handle to it. Now this isn't particularly important. I don't care about this CSRSS. Okay, conhost. Conhost didn't do the thing. It was cmd.exe that did the thing. So that's ultimately what I want to get to. And okay. So here's cmd.exe. We can see here it's getting a handle on example 5.1, but we can see here the desired access is read. So this isn't what we're looking for. Here it is. So here is our cmd.exe, again, create file on our binary. But here we can see that the desired access is delete. And the options are delete on close, share mode, delete. So what this means is this is going to delete the file once all handles to the file are removed, which basically means once the file is done executing. And the reason it has to do this is because, remember, the file spawned cmd.exe. Thus, while cmd.exe is running, so is the file. And you can't delete a file with open handles. So because it open handles, it had to set this delete on close disposition. And so this is where the actual file delete happened. So at this point, we have basically come to the conclusion of what static file and dynamic behavioral analysis can give us. We know that for whatever reason, the malware deleted itself, and we know exactly how it deleted itself. What we don't know is why. In order to learn why, we need to dig into the code itself, and that is what I am going to do in the next video, which I hope you will watch. So thanks for watching this one, and tune into the next one.